see here, it's modeling of HDL-based biorefineries for advanced biofuels production. The dean has appointed 3 members of the assessment committee for this PhD dissertation in evaluation and defense, and they have kindly accepted that, and we very much appreciate that. The 2 of them are external, so outside our university. One is internal, and he acts as the chairman of the assessment committee. I will present them one by one. I will start with the international. I don't know if he's connected with us, but it's Professor Dr. Martin Ginger. I hope I pronounced that right. He's professor in University of Utrecht University. He's professor in bio-based economy and energy and resources at Copernicus Institute of Sustainable Development. He obtained his master's degree in chemistry in Utrecht, and then his PhD also in the same university in learning renewable energy technology development. He's head of the group of energy resources at the institute, and he's leader of the bio-based economy research cluster there. His work encompasses various types of assessment of bio-based economy systems, including biomass potentials, resource assessments, both in developed and developing countries. He co-published and co-authored over 90 titles in peer-reviewed scientific journals. He is editor of several books in technological learning in energy sector, international bioenergy trade and mobilization of biomass from bioaerial and temperate forests, and he's editor of the bioenergy section in the journal Energies. He was also a member of several commissions and advisory boards and committees, including the Dutch Sustainable Biomass Commission. Then we have Associate Professor Lasse Wongo Clausen from DTU, welcome. DTU Thermal Energy and Mechanical Engineering. He obtained his master's and PhDs also in DTU in energy engineering. His research area is also in biofuel production based on thermochemical processes with focus on flexible polygeneration plants. He has 3 patents to his name, 2 on solid oxide cells and 1 in fuel cells from what I could see. As the chairman of the committee, the faculty has appointed Professor Henrik Lund. Professor Henrik Lund is a very renowned and the leading researcher worldwide. He's listed among ISI's highly cited researchers, among the top 1% of the researchers. He's also Thomson Reuters highly cited researcher within engineering since 2014. He is editor-in-chief of the International Journal of Energy in Elsevier. He's authored several books in renewable energy systems. So I think if anyone in the sustainable energy field kind of knows Professor Henrik Lund. On behalf of the faculty, I would like to really appreciate and thank you for the big effort that you've done in evaluating the thesis, and I would like to welcome everyone to this PhD defense. I'll say a little word on how this will be structured. We will have a 45 minutes presentation by Eliana of her PhD. Then there will be a 15-minute break, and then we will reconvene, and the assessment committee will be asking questions to Eliana on her project, and this will last to a maximum of 2 hours. So the session will end no later than 4 o'clock. And after the assessment committee has done the questioning, if there is time, then the audience and the supervisors will also be able to ask, and then we will close the session here. So please, Eliana, welcome, and you can do your presentation.
Thank you, Samuel. Thank you for the presentation, for the introduction, and good afternoon, everyone. I'm very happy to see all of you here. Today I'm presenting the results of my PhD project titled Modeling of HDL-based Biorefineries for Advanced Biofuels Production. So yes, I will just start. Sorry. will start by introducing the Ancestra project. This is an energy systems in transition. This is a Horizon 2020 project in which 15 PhD students were working on different aspects of the energy transition, dealing with technology, behavior, governance, and other aspects. So in Ancestra, we put together all these aspects to study the North Sea region, basically, in collaboration with partners from industry and also universities around the North Sea. So what brings us today here is the energy transition, and this is, of course, crucial nowadays because, as you see in the picture, energy contributes with the highest share of the yearly global greenhouse gas emissions. So what we want to do is to go from a system that works basically based on fossil fuels in a linear way towards a system that is more integrated and makes use of renewable sources in a more efficient way. This energy transition is powered by wind power. So this is the dominant resource together with solar. And there are sectors where we can already use electricity, such as heating, light transport, some industrial process heat as well, but there are other sectors where we need different solutions at the time. Here we're talking about indirect electrification, and it's mostly in the heavy segment of the transport sector that we need these alternatives for the short and medium term. Today, I'm talking about advanced biofuels. So advanced biofuels are one type of renewable transport fuels that are or that are expected to play a role for the European targets. What you see in the figure and in the right side of the slide are different targets that we have based on policies. So we had in 2018 the RED II setting a 3.5% target, and this year the Fit for 55 package, which included aviation and shipping in the targets. So this is very important, and also like blending mandates, specific and greenhouse gas emission reduction targets. This is the case for the sustainable aviation fuels. So we can see here that after 2030, we really need to scale up the technologies. We expect a high increase in the produced sustainable aviation fuels. Advanced biofuels are expected to play a role here to give support to the transition, while power to liquid fuels will play a role also, like after 2040, 2035. We will have a significant share of both types of fuels. So regarding the advanced biofuels technologies, we have different technologies right now on the research, also at demonstration scale, but not many of them have reached commercialization, which is going to be crucial to meet the targets. And my focus today is on the hydrothermal liquefaction technology, which I point here. And I'm going to explain it right now in the next section. So HTL comprises two main steps. In the first step, we have we process biomass in the presence of water at high temperatures and pressures. And this way, we use water as a medium of the chemical reactions to produce a biocrude. In a second step, we use this biocrude and we use hydrogen in order to improve the qualities of the fuel and to make it suitable to be used as a transport fuel. Along the process, we have other products that are, of course, very interesting from a point of view of system integration, and we would like to also know how to use them in an efficient way. For going to a commercial stage, of course, there are very different aspects that we need to consider for the technology to be viable. So there is sustainability of the feedstock, which is crucial when we talk about biomass-based technologies. We also have the greenhouse gas emission reduction, the economic feasibility, so the minimum fuel selling price that we offer, fuel specifications, of course, very important, policy regulation, and also social acceptance, not the least important of this, of course. All these aspects are very important, but today I'm focusing more on the economic feasibility and also on the greenhouse gas emission reduction. So my research is in the study of different aspects of the HTL technology that can contribute towards commercialization in these two main aspects of the technology. Yeah, what we have learned from literature in the past years is that the technology is actually very flexible in terms of the feedstock, so we can treat a wide range of biomass. Lignocellulosic material is very abundant type of biomass, but also urban wastes are very interesting from the point of view of waste valorization. In terms of the emission reductions, literature has also shown that we can target approximately 65 to 85% reduction, and also that the minimum fuel selling price is in a competitive range between 0.5 and 1.3 approximately euros per liter. So as I was mentioning before, we're interested in looking at all the other products that we have from the process, and also what are the potentials of this technology in an integrated energy system perspective. One of the products is the carbon dioxide. So this is an interesting product for carbon capture and utilization or carbon capture and storage applications. We know that Power-to-X and also negative emissions technologies are going to play a role for the energy transition. And right now, there is lack of studies on CO2 capture from the HTL gas. So this is something that I studied in my PhD. And also, the excess heat that is produced in HTL, we could use it for sector coupling. So this is also another aspect that has not been studied in so much detail. This brings me to my research questions right now. So first of all, I look into how to model HTL and how to improve or how to have better or more reliable estimations, particularly on energy balances and the heat from the process. The second point is the implementation of carbon capture from the HTL process. And last, I look at these aspects to study or to apply them in case studies for two different kinds of feedstock, lignocellulosic materials and also sewage sludge, looking at the potential of the technology in the context of negative emission and also waste valorization. This slide summarizes the methodology I used. So basically, it was a lot of literature study at the beginning. Also, I used experimental data in-house, so produced in the group, and also what has been reported. In the modeling side, a lot of process modeling, and also for the economic evaluation and the environmental impact, I used all the results connected. And yeah, I made these 4 objectives, which are linked to my 3 research questions. And these, I have them published in journal publications. So in paper A, I present the results of the modeling part of the HTL process. Paper B comprises the modeling of carbon capture from the 2 feedstock that I use, forestry residues and sewage sludge. Paper C, it's the case study on centralized HTL biorefinery with carbon capture. This is based on forestry residues. And in my last paper, I studied the distributed HTL biorefinery for waste valorization using sewage sludge. I will go now through these 4 publications, and I will present what I think are the most important aspects of them. So in paper A, I'm going to talk about how to model the HTL. Highlights from this publication, from this study are we developed a methodology that we can apply to estimate more accurately the enthalpy of formation compared to the traditional route. I'm going to talk about it a bit later. Also, we developed multi-objective optimization for selecting the model compounds in the biocrude. And something that is very important is the availability of these models open access. So these are also applicable to other types of biomass and also other types of processes with unknown exact stoichiometry or kinetics. So one big question here is, how do we model HTL? This is a typical configuration of HTL. So we start with a biomass slurry. We need to bring that to a high pressure and high temperature. And then after the reaction happens, we can use the high temperature products to heat the feed, and then we obtain our products after separation. So in this process, we have very complex materials. We start with biomass, which has a complex composition, and we end with a biocrude product that also has a quite complex composition. So there are thousands of molecules present here that challenge the modeling, and what we have seen in literature is that predictive modeling is difficult, it's hard. So for the purpose of energy system integration, we are more interested here in a more reliable estimation of the heat, right? So in this case, we kind of zoom out a little bit and we focused on the overall thermodynamics of the process, and therefore we focused then on the enthalpy estimation of the streams. This we do based on experimental data on product yields and composition. And we implement this we can implement this in different modeling tools. I will start with the biomass enthalpy. Typically, the enthalpy is estimated based on the high heating value or low heating value. What this figure shows is that really a very small error in heating value, which is in the x-axis, will cause a significant error in the heat of formation. So we want to avoid this when trying to estimate the heat in the process, and therefore we developed here a correlation that allows a more accurate estimation, which is the one I highlight there with the blue. So it's the Lozano correlation, and that you can use it for a more accurate enthalpy estimation. It's directly from the biomass composition, avoiding the heat of high heating value route. Now we go to the biocrude. As I mentioned before, it's formed by many compounds. So what we need here is to select components that are representative, or that in a mixture can be representative of the bulk properties of the biocrude, right? So then we developed multi-objective optimization, and we want to reduce the error in the enthalpy by changing the composition of the model compounds. So what you see here in the picture is what we had initially from experimental results, and the optimized composition, which allow us to decrease the error in the enthalpy of formation and to keep more or less the errors in the other properties that we know within 20%. But again, our focus is on the enthalpy, so this is considered a good alternative for reliable energy balances. So we want to set the overall thermodynamics here. In the left side, you see for all the input and the output of the process. We compare that with what we know from experiments. We see a good match between what's modeled and what we know. And from there, we estimate the heat demands So what's in the HTL, the heat of reaction, and also the heating and the cooling requirements. So the results show that actually the heat of reaction it's quite low compared to what we need for cooling and what we need for heating. So yeah, the variations are explained by the changes in the composition, so the changes in the heating values and experimental data. But overall, we are talking about 10 times less the heat of reaction compared to what we need for heating and cooling. So this is yeah, an important conclusion from here. We use then this to see the big picture of the process. What you see here is having an input of 100 megawatts of biomass. We have the hydrogen, electricity also, and we have as an output of the process a hydrotreated biocrude, which contains most of the energy that we put from biomass. And also we have in the lower part of each diagram a loop that represents the heat integration between hot and cold streams, and that represents also that we can actually be a self-sustaining heat for the forestry residues case if we use the gas. So this is the small line that you see going from the gas to the heat. We can use the gas in the forestry residues case to be self-sustaining heat, and in the sludge case, we need more heat to supply to the process. And yeah, we see here overall the biocrude is the main product in terms of energy. So right now I will focus on the gas phase and carbon capture from it. I will start again with some highlights from the publication, from the study. We evaluated the Selexol technology. This is based on physical absorption, and we identified it as a cost-effective method for CO2 capture in the forestry residues derived gas. Not recommended for the sludge gas. I will talk about it later on. However, the process delivers a relatively high purity and also recovery. One limitation is though the hydrocarbon co-absorption. So this impacts the process because decreases the energy potential of the combustible gas that we want to use for heating, and also decreases the purity of the CO2 that we want to use in another process further on. Also, physical absorption brings opportunity for hydrogen recovery in the case of the forestry residues gas. So I'm going to talk more about the composition of the gas here. You see different bars representing minimum and maximum in the case of the forestry residues and also in the sludge case. We see that for the forestry residues derived gas, we have a high CO2 composition between 60 and 80%, more or less. It's even higher in the sludge case. It's interesting in the forestry residues, we have a significant content of hydrogen. So what we would like to study here is how to separate the CO2 from the combustible gas and still use the combustible gas for heating the process to supply the internal heat demands. Well, there are a lot of carbon capture technologies that have been studied at different TRL levels. We have the most commercially available are the absorption process, either with chemical or physical solvents. So in the case of HTL, as I already showed, we have a high CO2 concentration in the gas, and also we have a high upstream pressure because of the conditions that we need in the process. So this favors the selection of physical solvents. There are different types of physical solvents that have been studied. Yeah, here I show some of the main properties. CO2 solubility, vapor pressure, which has an indication of how volatile, how are the chances that we have to lose some of the solvent in the process, and also viscosity. Previous literature have favored the Selexol. Well, this is a mixture of glycols, and it's under the commercial name of Selexol. the previous literature has favored this over the other solvents, so we choose this one for the study. Here you see a simplified diagram of how the absorption process works. We, in the first step, need to remove condensables from the HTL gas because it's a wet process, so we need to remove water and whatever is soluble in water beforehand. Then we use the solvent to separate the CO2 and to leave the other non-soluble gases, which are mainly hydrogen, methane, and carbon monoxide. Separated that from the CO2, we regenerate the solvent by means of expansion. So this is an advantage of this process that doesn't require heat by default. And also, well, afterwards, we need to cool and compress the CO2. Here, yeah, what I was mentioning, solvent regeneration by expansion, this means lower energy requirements in the process. The solvent is stable, and it allows for a further study in hydrogen recovery. Here you see the results. We have the HTL gas phase compared to the outlet products here, so the combustible gas and the CO2. So you can see here that it's the separation of the combustible gases from the CO2 is quite efficient for the forestry residues case. We obtain a CO2 product that has a quite high purity. So for this base case was above the 95%. And the combustible gas has enough potential for supplying the heating demands in the process. So this is what you see in the right axis. From the previous section, we more or less talk about 2 megawatts per 100 megawatts of input biomass that we need, and the combustible gas has still enough potential to supply this heat requirement. Here I present the CO2 composition for all the ranges of the ranges evaluated, and actually, we see that in all cases for this configuration, the geological storage requirement is met, so it's above 90%. However, we don't meet the 95% requirement that is that is typically required, the requirement for pipeline. So we wanted to see if, looking at a different configuration, we could have a higher CO2 purity. And we managed to do that. We changed a little bit the configuration. We included another absorption step. And you can see here that the composition actually increases. However, there are other challenges here, which are the production of other type of compounds. This is because we need to include combustion here, but I'm not going to go into details of this configuration. I will go to the cost. So this is the Monte Carlo results of the single and the two-step absorption. We can see here that for the single step, we have quite a good cost of capture CO2. It's between 40 and 53 euro per ton, which is in a competitive range compared to the emission trading system at EU level. So this is a good result. For the two-step absorption, we had quite higher price. And the variations are mainly due to differences in electricity price and labor cost. Here you see the breakdown of the costs. So electricity is a big part, what is in the purple color here. However, the revenues from heat can decrease the costs. We also wanted to see the results in comparison with other industries or the CO2 capture from other type of processes. Also to see that that is in line with increasing CO2 concentration, we expect a decrease in the cost. So more or less we are here. So the result is it's in line with this with this observation. So now I will explain, or I will explain the results of the paper C and paper D, which are the case studies in which the modeling is included. The modeling is used to evaluate different configurations. So first of all, paper C, we look at a centralized HTL biorefinery with carbon capture, again based on forestry residues. So this is a bit different than the previous case because we have the select sol. So as I already explained, we can take the gas phase, separate the CO2 and the combustible gases. But in a centralized scheme, we are also interested in hydrogen recovery because we use hydrogen in excess in the upgrading process, and this needs to be recovered for the economy of the overall scheme. So we use select sol here for a dual functionality, separate the CO2 and also clean the hydrogen for the upgrading step. I will present some highlights again. The cost of the CO2 capture, including hydrogen cleaning, is estimated in €64 per ton, so it's a bit higher than what I presented before, but it's because of the hydrogen add-on. Carbon price and excess heat revenues can compensate the cost. I will show you more in detail later on. And the impact in the minimum fuel selling price is estimated between -2% and 5%, so it's within the 5% increase. From the environmental assessment, the HTL process with carbon capture and storage can reduce emissions by 100 to 113 compared to the fossil baseline. So it has potential to perform as a negative emission technology based on the results. So this is the addition or the modification of the select sol that we wanted to study here. We include an extra absorption step. So if you remember from the previous process, we used that solvent here for the CO2 capture. We wanted to also use that solvent to clean the hydrogen. What is the advantage here is that we could purify hydrogen at a high pressure. But a limitation is in the methane impurity. So the fact that methane is not soluble in the solvent, in the select sol solvent, means that we cannot really remove all the methane from the hydrogen. So it will be still above the threshold for commercial catalyst, which is indicated in the order of 500 ppm. But we made the energy balance of the process. So you see the main energy flow here going from woody biomass to hydrotreated biocrude. There is a high efficiency towards the biocrude again. And the second, the other energy flow here, which is important, is the hydrogen. So the fact that we couldn't remove all the impurities needed for the upgrading would mean that we need to purge some of it. But still obtaining a combustible gas that could cover most of the hot utility in the process. So this would reduce significantly what is the heat utility requirement here. And what you see below, the slope represents the heat integration between hot and cold streams. So we could also have excess heat for energy system integration if it's needed. Looking at the cost, we have the cost of the HTL baseline in the first bar on top. And then we estimated the cost when we added the select sol. So we can see here that without revenues, we will have an increase in the order of 8%. However, when we included revenues from the excess heat and also the CO2 credits, the difference is reduced significantly. This is also shown in the Monte Carlo results. So it's kept within the 5%, this increase of the carbon capture. And here you see the values also in euro per gigajoule. In terms of the environmental performance, we have a standard HTL with approximately 85% reduction in greenhouse gas emissions. This is in agreement with what has shown previous literature. When we included CCS, we reduced that. We see, however, that the main factor here is the hydrogen. So this is because electricity is not 100% clean yet. So we have some emission factors from the electricity usage for hydrogen. So in the scenario with when we have 100% green electricity, of course, we would expect a better performance as negative emission technology. And here I wanted to compare with other studies on hydrothermal treatment. There are not so many at the moment, but this shows that it's more or less in the range or what other researchers have shown. So yeah, minus 20 to minus 50 shown here, and in this case we have a bit lower, but it's also because we increase the energy return of investment, so we have a little bit more biocrude compared to other studies. Yes, so this is the last paper that I'm going to talk about. In this case, I will present the study of a distributed HTL biorefinery. This was a case study developed in the Netherlands. It's also during my study abroad in the Netherlands that I was developing this. And here again, we focused on techno-economic and also environmental study to compare HTL for valorization of sludge with the business as usual case, which is mono incineration in the Netherlands. So first, a little bit of what is the status on sewage sludge treatment. There are different methods that are applied right now for the disposal of the sludge. And this varies a lot across EU. So in the Netherlands, the main method by far is the mono incineration. We know that key technology aspects here for the disposal of sludge is the destruction of contaminants. So we have pharmaceuticals, we have other types of organic components in the sludge. And also phosphorus recovery is going to be key for the technology to be viable. This is because we are running out of phosphorus basically worldwide, so we need to recover phosphorus from the sludge. Mono incineration, it's a relatively good method because, of course, it allows to destroy contaminants, and also it can be coupled with phosphorus recovery. However, it's quite costly. So this price that you see here is what more or less we know for the Dutch case. So it's in the order of 100 euro per ton. Highlights from this study is when we compare HTL with mono incineration, we see that it has potential to be more economical. And also, in terms of environmental performance, it can be about 3 to 4 times better based on LCA analysis. So here we talk about distributed plants, and it's important to say why we took this approach. So it's because sludge is generated in wastewater treatment plants, and there are quite a lot of these in the Netherlands, quite dense populated country. So it's already produced in a quite distributed manner. From previous literature, we have seen that actually we need more or less big wastewater treatment plants to implement this individually. So if we look at the Netherlands case, this capacity here would match with more or less the 60%. So in this case, a distributed configuration, when we gather sludge from all the smaller wastewater treatment plants, will allow to harness the potential, the whole potential in the country. This Sankey diagram shows the mass balance. So we took the statistics from 2018 from sludge production. And based on this and based on experimental yields, we could estimate more or less the potential for hydrotreated biocrude is in the order of 50 kilotons per year. We also have a significant flow of mineral product from which we can recover phosphorus. And yeah, these are the main two products that are interesting here. Regarding the cost, so what you see in the first bar in the positive side is all the cost associated with the process in the HTL. And in the negative, we have the cost of the sludge, which is negative because you get paid by treating the sludge. So more or less, these two bars compensate. So at the end, we're talking about a quite low minimum fuel selling price for the HTL biocrude. Then when we translate this to the upgrading, to the hydrotreating step, we of course see an increase in the cost. But again, if we take into account the sludge gate fee, it can be very low. So definitely this parameter is the one with the highest impact in the cost and is the most sensitive one. This is the cost that we estimated using a gate fee of 100 euro per ton. And it was also interesting to see that actually the share of transport for this distributed configuration was actually relatively low. So this means that we could go for larger plants, regional plants, to further decrease the minimum fuel selling price. This is how the Monte Carlo results look. So again, we have a quite good minimum fuel selling price, and in some cases it's negative. So in these negative cases, we could say that actually HTL can be more economic disposal method compared to mono-incineration. And we have an increase when we hydrotreat the biocrude, but would be again quite competitive if we take into account the negative price of the sludge. In terms of the environmental performance, we see here, we look at the business as usual case, which is the mono-incineration. The positive of the positive side corresponds to actually sludge incineration, but in the negative, we have the avoided products. So in this case, for this is a plant that is one of the two main plants in the Netherlands, and they do carbon capture and utilization. So this makes the process quite positive actually, and also they claim they avoid other products such as products for pavement or products that can be used in other sectors. So when you avoid a fossil product, you of course have a very positive performance, and this also we see in the HTL. So the main positive factor here is that we avoid a fossil crude, a fossil product for the marine sector particularly. So this greatly compensates the positive emissions that we have in the process that are mainly attributed to the hydrotreating because of the hydrogen requirement. And finally, the conclusions of my study. I wanted to come back to these aspects of the technology viability. So in the side of HTL modeling, we developed tools that allow a more accurate thermodynamic estimation. And this can contribute for the economic feasibility studies. So can be used for other types of biomass and can be used for different process configurations as well. We also, of course, have some recommendations for future work here. Extension of experimental data set, it's very important. I focused mainly on heat, but also electricity it's very important in the process, and electricity requirements are likely to be underestimated in this study. So we will need better viscosity data and so on to have more accurate results here. And also to expand the energy integration analysis to exergy, so we could look into other types of energy integration in the process, and this could be very important. And also the aqueous phase could be better modeled here. We need more experimental data, and we need other type of model that takes into account non-ideal behavior of the aqueous phase. Regarding the carbon capture, we can say that based on the study developed, this is a technically feasible option, and it's suitable for woody biomass, derived gas. We recommend that maybe other carbon capture technologies could be studied further in order to make a comparison, and also because, as I showed, in order to have a very high purity of the CO2, we need to increase cost based on the technology that we studied. So maybe a different technology could provide a higher CO2 purity stream at a lower cost. And also experimental validation, it's important here. And regarding the techno-economic and environmental assessments, for the centralized case, we can say that the HTL has potential to perform as a negative emission technology with an increase in the minimum fuel selling price within the 5%, which is, again, not too bad. And for the distributed configuration, this also seems competitive with current mono-incineration fees for the case study, and also shows a positive performance, environmental performance compared to the business as usual. Recommendations, looking into more location-specific case studies will bring more detailed and more accurate results. And also optimization of size location in the distributed configuration could contribute more to more reliable results. Thank you very much for your attention, and yeah, this has been all in my presentation. So thank you.
Thank you very much, Eliana. Now we have a short break for around 10 minutes, I think. We will come back at 2. I think there should be some coffee outside. We can't guarantee that. But, yeah, see you in 10 minutes. Okay. Thank you. Fantástico,
Muy bien.
Gracias.
Felicidades.
Gracias.
Muy bien. Me encantó, de hecho, tu trabajo. ¿Eh? Sí.